MS Ramaiah University of Applied Sciences.
Hello students, let us discuss on determination of copper present in brass sample. When we hear the word brass, we can recall the brass articles in the kitchen, brass band set, etc. Then you may be also wondering why we should know the percentage of copper in brass. Let me explain you about this. Brass is an alloy of copper and zinc. It also contains small amounts of tin, lead and iron. Typical percentage composition brass alloy is copper 50 to 90%, zinc 20 to 40%, tin 0 to 6%, lead 0 to 2% and iron 0 to 1%. Since the variation in copper controls the mechanical properties such as malleability and ductility of brass alloy, it is must to know the copper content before the alloy is used for specific application. Free cutting brass such as C38500 or 60/40 brass is used in nuts, bolts, threaded parts, terminals, jets, taps, injectors, valve bodies, balance weights, pipe and water fittings, etc. Gilding metal such as red brass or C22000 is used in architectural fascia, grille work, jewelry, ornamental trim, badges, door handles, marine hardware, munitions, primer caps, pen, pencil and lipstick tubes, cable glands, etc. Iodometric determination of copper is based on the oxidation of iodides to iodine by copper 2 ions, which gets reduced to copper plus, which are rapid and quantitative. Amount of standard sodium thiosulfate solution required to titrate the liberated iodine is then equivalent to the amount of oxidizing agent Cu2+. Liberated iodine is titrated against sodium thiosulfate using starch as indicator towards the end point. Procedure: weigh accurately about 0.05 gram of the given brass sample and transfer it into a clean conical flask. Add 2 to 3 centimeter cube of 1:1 nitric acid. Mixture becomes green owing to complexes of Cu2 plus and NO2 being formed, and brown fumes are evolved. Cover the mouth of the flask with a glass funnel and boil till the alloy dissolves completely. Add 10 ml of ion exchange water and gently boil till the brown fumes of oxides of nitrogen are expelled completely. Add 1 gram of urea and continue boiling for a few minutes to expel the nitrous fumes. Cool and add 1 test tube full of ion exchange water. Add aqueous ammonia dropwise to the solution prepared above until a pale blue precipitate of copper hydroxide is formed. To remove mineral acid, dissolve the precipitate by adding dilute acetic acid and 1 test tube full of 10% potassium iodide. Titrate the liberated iodine against standard sodium thiosulfate solution till the mixture turns straw yellow. Add 5 drops of starch indicator and continue the titration till the blue color just disappears and a white precipitate is left behind. Repeat the procedure with the fresh samples of brass. Following are the steps involved as explained till now. Brass sample in conical flask. Brass sample plus nitric acid. Brass sample plus nitric acid, brown fumes of oxides of nitrogen, brass getting dissolved. Brass solution plus urea boiling. Cooled brass solution plus ammonia solution. Cooled brass solution plus ammonia solution and acetic acid. Cooled brass solution plus ammonia solution plus acetic acid plus potassium iodide. Reaction mixture plus sodium thiosulfate, straw yellow. Reaction mixture plus sodium thiosulfate plus star solution. Reaction mixture plus further sodium thiosulfate.
Hi students, today we are going to learn one more volumetry experiment. The aim of the experiment is to find the percentage of copper in given brass sample. So what is brass? So brass, you can see that these brass pieces are there. So in this we are going to find out the amount of copper. Means it is brass is an alloy of copper, zinc, lead and tin in some percentages. The major percentage will be copper and zinc. So in this we are going to find out by iodometrically how much copper is present in this brass piece. So we are going to find out the amount of copper in the brass piece. So we have a brass pieces here, brass piece, a known quantity of brass piece. You have to use it for the analysis. We have funnel, glass funnel to transfer the standard solution to the burette. Conical flask where we are going to do the reactions, and test tubes to add the acetic acid, ammonia and all, and a dropper to add the nitric acid. The burette, a 50 ml burette where you are going to take the standard solution. Standard sodium thiosulfate, it's a reducing agent. We are going to use it as a standard solution here this time. So we are not going to prepare the standard solution. Standard solution will be given to you. Starch as indicator here, freshly prepared starch solution. So this is used as an indicator in your iodometry titration. Potassium iodide, because it is an iodometry titration, we are going to add potassium iodide where iodine will be liberated, and that you are going to titrate against the standard sodium thiosulfate. Acetic acid to maintain acidic pH. Ammonia, 1:1 ammonia. So ammonia is used to neutralize the nitric acid which has been used to dissolve the copper piece. Urea to destroy the oxides of nitrogen, you are using this urea. And nitric acid, concentrated nitric acid to dissolve the brass piece, or you can say it as copper pure brass piece. You are going to dissolve using the nitric acid. Lastly, you can see the wash bottle to wash the glass apparatus. Here we are taking distilled water. After tap water, you have to wash with the distilled water and dry it. Let us start the experiment. So as usual, we have to start with the washing of the glass apparatus. So the glass apparatus, that what we want is a burette, a funnel and a conical flask. So wash with tap water. Wash with tap water. The funnel also to be washed with tap water. And the burette. Washing with the tap water, then you have to rinse with the distilled water. So as you have seen, it has to be rinsed from both the ends. The funnel also to be washed and rinsed. Distilled water, the conical flask also. So for this experiment, you have to use little bit clean and dried conical flask. So dried because your nitric acid should be not diluted. So you have to try to remove as much as possible. The water has to be removed. This has to be taken for the experiment. So we have to rinse the burette with thiosulfate solution. The standard thiosulfate solution is there. Standard thiosulfate solution. So as I said earlier, you are not going to prepare the thiosulfate. Thiosulfate with a known normality will be given to you. Add some quantity. Rinse it up. Lift from both the ends. Okay, now it is rinsed. So I will fill the thiosulfate and keep it ready. So watch carefully, some air gap should be there always. Take it above the mark. So I can take it above the mark. So keep the standard solution aside. Now adjust it to 0. Okay. Now your thiosulfate solution is there in the burette. So it is the lower meniscus should be touching the 0 mark. So we have to take a known quantity of copper piece. So I have transferred a known quantity, so you should be knowing the weight of the exact copper piece, your brass piece sample. You should be knowing what is the weight of exactly the transferred, and transfer to your conical flask. So this conical flask should be dried as much as possible. It should be dried. Then you have to dissolve. Since you are doing it in volumetry, you can't do the solid sample. You have to dissolve it. So to dissolve it, you are using concentrated nitric acid. So be careful with the nitric acid. It's concentrated one. So when you are adding it, so take 3-4 drops, add exactly on the top of the copper piece or brass piece. And see that the brown fumes are coming out. The brown fumes is oxides of nitrogen we are expelling out, and the brass piece is slowly dissolving in the nitric acid solution. So you can see there is no effervescence now. It has been completely dissolved. Brown fumes are there. This is oxides of nitrogen. We have to destroy the oxides of nitrogen. So to destroy the oxides of nitrogen, we are going to add urea, little bit of urea. 1 spatula of urea. We are adding 1 spatula of urea. So if oxides of nitrogen are present, it works as an oxidizing agent, and that will oxidize the potassium iodide. So we want the oxides of nitrogen to be destroyed. So we are adding urea and 1 test tube full of water. And 1 test tube full of water. So I have added urea, and the urea has been dissolved now. So this has to be boiled for 2 to 3 minutes. So I am keeping it in a Bunsen burner. So you have to boil your copper solution. It has been dissolved now I added urea, so it has to boil a little bit so that completely the oxides of nitrogen have been destroyed. So I am keeping it on a Bunsen burner, so to adjust the Bunsen burner to blue flame and then keep it so that you can see that it boils very fastly. So you can see the bubbles are coming out, 2 to 3 bubbles, it's good enough. So hold it using the cloth. Now you can see there is no brown fumes. All the oxides of nitrogen have been destroyed as into gases and carbon dioxide gases. Some bubbles are coming up, so it shows that it has been completely boiling. So it's enough, 1 to 3 bubbles. Shake it thoroughly. Now you have to cool the solution, bring it to the room temperature. So you can do that under the tap. So I am cooling this under the tap. So be careful. So you have to cool it under the tap. Just hold your left hand so that you should be in a care. Okay, it is almost cool. Thoroughly cool it, so otherwise we will be not able to see the next reactions will be not happening properly. So you have to cool it to the room temperature. Usually we can feel it by touching from this side. Yeah, it's almost cooled. If it is not cooled, just 2-4 minutes you can swirl it, it will completely cool down. So now it is cooled down. Ensure it thorough cooling, means the cooling has happened properly by adding 1 more test tube of water. Now it has been completely cooled. So the solution has been cooled. So ensured. Now we are going to add ammonia. Ammonia is added to destroy the nitric acid. If nitric acid is there, it will oxidize the iodine to iodic acid and also the potassium iodide to iodine. So we want only the copper to oxidize the potassium iodide, not the others. So I am destroying it by adding ammonia. So you have to add ammonia in a dropwise fashion, slowly with swirling. So until how much you have to add so that you can see the light pale blue PPT should form. Okay, if PPT has not formed, it has become completely dark blue, then we have to discard the reaction. So this PPT is cupric hydroxide. So this will not interfere in your reaction, so this can be continued further. But it forms a cuprammonium complex, it will be dark blue in color, then you have to discard the reaction. Otherwise, if it is not forming in PPT, so then also you have to discard the solution. So now it has been neutralized, the nitric acid has been neutralized, then it is forming cupric hydroxide. So this PPT has to be dissolved and also you have to maintain the pH, so that's why I am using acetic acid, 3/4 of acetic acid is enough. Almost 3 ml of acetic acid to dissolve the PPT. So now you can see the PPT has been dissolved, so the copper is in +2 state only. Still the copper is in +2 state. So the PPT has been dissolved by adding acetic acid. So 3 ml of acetic acid is good enough to add it. And this acetic media is necessary for the reaction of thiosulfate versus iodine. So as I said, it is an iodometry titration. So now I am going to add potassium iodide. Iodometry means we are going to liberate the iodine inside the reaction mixture. So we have to add known excess quantity of potassium iodide. So we are stabilized here. So half test tube of potassium iodide is good enough for the reaction. So we have to stabilize it if it is unknown quantity. So we have stabilized it for an half test tube. So before adding potassium iodide, so we have to think, we have to take a care that thiosulfate should be ready. Since as soon as you add potassium iodide, iodine will be start to liberate. So the liberated iodine you are going to titrate against sodium thiosulfate. So if you add iodine and leave it for some time, the iodine will start to escape. So you have to take a care that before adding potassium iodide, thiosulfate should be filled inside the burette. So now for me, the thiosulfate is ready. It is in the 0 mark. So I have added potassium iodide. So we can see it starts to liberate the iodine very fastly. So iodine we can see slowly the iodine is getting liberated. Start the titration. So you have to titrate against standard sodium thiosulfate till it becomes light yellow in color, or we can say the pale yellow or badam milk color it will become. So until that you have to titrate. So you are not using the starch at the beginning, you are going to use the indicator starch at the near to the end of titration. So you can see it is becoming lighter. Now it is light yellow. So it should become pale yellow. Yeah. You can see now it is pale yellow in color. So at this point you have to add the starch. So one complete, at least 5 to 10 drops of starch you can add. So you can see it becomes blue color. The blue color is because of the starch iodine complex. So now we have to see the end point is colorless. We will be able to see the white PPT. So blue color to white PPT should be remaining. The white PPT is due to C2I2, which is a byproduct of reaction of copper with potassium iodide. So that will be remaining as such. So you will be not able to see the colorless, it should be white PPT. Yeah, we can see the blue color is disappearing, it is becoming white. Now you can see. So if it comes back, the blue color, if it's coming back, then you have to add a little bit more of thiosulfate. The dropwise fashion, 3-4 drops. Still colorizes. Still light blue is there, so we can continue the titration. So So now it is not turning back to blue color. So the white PPT should be remaining as it. The white PPT, what it is remaining is Cu2I2. So you have to note down what is the amount of thiosulfate has been consumed. Remove it out, take it to the eye mark and see what is the amount. This is 24.6 ml has been consumed. So now what you have to do is throw this solution wash with plenty of water. Wash with plenty of water. So after completing the titration, you have to wash with little bit of ammonia. So you can add ammonia a little bit. So because Cu2I2 is insoluble in water, we have to add a little bit of ammonia. So Cu2I2 will dissolve. Otherwise, that will be interfering in your next reaction also. Wash thoroughly with water, plenty of water, because ammonia should be not interfering in your next reaction. With water, tap water, dry it as much as possible. Okay, now the cleaned conical flask is ready, so you can take the fresh copper paste and do the second titration. So depending upon the copper pieces, copper 1, copper 2 and the amount of thiosulfate consumed for the each samples, you can calculate how much of copper is present in the given brass piece. So this completes the experiment.
At MSR UAS, we spark your imagination unlike any other.